everyone, welcome to APS Deep Academy and this is your mentor Swati Joshi. In last class, we studied about junction field effect transistor and channel and its working. We already discussed the VI characteristics. Now in today's class, we will study transfer characteristic of junction field effect transistor. Now we are considering the N-channel JFET here. This is the basic diagram of N-channel JFET where the biasing battery VDD and biasing of gate to source voltage VGG is there. So in this diagram we can see that this is the VGG which is connected between gate and source and it is making the gate reverse bias. So negative terminal is connected to the gate and positive terminal similarly connected to the source. And we know that source is grounded here. So source is at 0 volt potential. So we can see that with this the help of this negative battery, the gate is negative. Let's consider minus 1 volt. And this is the biasing battery VDD. In our case, let us consider it at 5 volt. We know that in our earlier session also that in between PN junctions a depletion region forms. So this is the depletion region. And the width of this depletion region clearly depends on the biasing battery and the gate voltage, gate to source negative voltage. So that we already discussed that this layer is widened here. In upper side it is more wide and then it is becoming little sharp here. Similarly, upper side it is high and it is making little sharp here. So here in between this the channel is formed. So this is the channel where electrons flowing and current ID is flowing in this direction from drain to source. This is the voltage level which is VDS drain to source and it is similar as VDD. So the voltage potential difference of VDD and VGS is same. All the earlier configuration where I teach you that what happening with this width we already discussed in our earlier classes. You can check it from the playlist. So here quickly we will review what is happening here, how this ID current is producing. So due to this biasing battery VGG, what is happening? It is negative. It is making this PN junction more negative. So the width of the PN junction, this here, this is N and this is P. So width of the depletion region of this PN junction is already very much high. So, and when we apply this VDD, this width is even more increasing. But what is happening here? This 5 volt, this positive 5 volt is traveling towards this channel and it is not traveling suddenly but it is traveling gradually. So here it is 5 volt and till below it is somewhere it is 4 volt, 3 volt, 2 volt, 1 volt and similarly here 0 volt. So what is happening due to this ununiform voltage division, this layer, this depletion region is also not uniform. So in upper case it is little wide and in lower case it is thin. So this is the formation of the channel in N-channel JFET. So this is the whole working I already explained so many times in our earlier classes. Now we move forward to the VI characteristic and the transfer characteristic of JFET. So this is diagram of VI characteristics. So here this area, right side we can see this is VI characteristic and this left side, this is our transfer characteristics. So transfer characteristics is graph between IDS and VGS. Okay. So here two things we have to consider, that transfer characteristic is a graph between IDS and VGS. Similarly, the VI characteristic curve is drawn between IDS and VDS. Okay. Similarly, here we can see that VGS is the biasing voltage which we consider here. Here VGS is the biasing voltage here. So it is similar to VGG and VDS is our biasing voltage which is similar to VDD. So these two voltages are there. Okay. So in output we can see that if output current ID is drawn between the graph of IDS is drawn between VGS and IDS, we call it transfer characteristic. And if this graph is drawn between IDS and VGS, it is VI characteristic. So in last class we already discussed the VI characteristics. Quickly we will review what is happening here. So current is increasing when we increase the VDS Let's suppose we are increasing the VDS and current is increasing at a particular manner, it is saturating, and we consider that voltage is pinch off voltage where the current saturates. So this voltage we are considering it as pinch off voltage. This voltage is our pinch off voltage. Similarly, if uh, here these few values of VGS is giving. First, we consider VGS case where VGS is 0. We already discussed in earlier class when VGS is 0, this voltage. Okay. This VGS first it was 0. So what is, and then we will increase it -1, -2, -3. Similarly, this graph is drawn like that. First the VGS is 0, then we will get the maximum current ID here. Okay. At this point we are getting the pinch off. So this is the value where we are getting the pinch off. So this is the value BP. Now after that the current is saturated. When we increase the VGS, okay, here the let's suppose it is -1 or it is -2 here. Let's suppose it is -3 here and it is -4 here. So when we increase the VGS, the current is gradually decreasing and pinch off voltage is also decreasing. So we are getting the pinch off voltage at less value here. Let's suppose this is, we are getting the pinch off at 5 volt. So here we will get the pinch off at 4 volt, here at 3 volt and here at 1 volt. So what is happening here when we increase the VGS? When we increase the VGS, more negative VGS is negative value. So when we increase the VGS from 0 to negative, okay, here we can say negative. This is negative area. So when we increase the VGS from 0 to negative, the current is gradually decreasing and the pinch off voltage is also decreasing. Okay. If we are getting a pinch off at plus 5 volt when VGS is 0, so we are getting the pinch off at 1 volt when VGS is -4. Okay, so this is the whole structure of input VI characteristics of the and channel JFET. Here, three discuss the regions of that. So this is the saturation region. Here to here, where the current is saturating. After this pinch off, the current is saturating. It means the maximum current we achieve, and after that VP attain, the current is saturate or it is not increasing that much. So this is our saturation region, which is generally considered as active or working region of the transistor, FET transistor. And this region is considered as off, channel off. Okay, because here what is happening? The off situation means if I talk about the switch as we studied in switching operation of BJT, similarly for FET also, if we consider it as switch, then it is the off state of the switch and saturation region is the active region or the on state of the switch. This is the linear region where current is gradually start increasing. So this is the linear region. Okay. Now here one region is also there. It is not shown in the graph, but this region, this we call ohmic region. Ohmic region. Okay. This ohmic region is where the resistance value is high or very high resistance. We can also consider it as insulator, but we will not consider insulator because it is a semiconductor device. So this is the ohmic region where we get the maximum resistance of this output. So it is also considered as off state. And after that, we know that when this maximum saturation limit is happening, after that the breakdown occurs. So after that the current will increase exponentially. So these current are increasing exponentially. And in earlier class we know that the breakdown voltage is also shifting towards the left when we are increasing the VGS. So when VGS is 0, let's suppose breakdown is occurring at 20 volt. So when VGS is -4, so breakdown is occurring at 15 volt. Okay, so the breakdown voltage is also shifting towards the uh, uh, left side. Okay. Now this region is our breakdown region, which is also considered as cutoff of the transistor. Okay. So transistor will not work in the breakdown region also. So this is the VI characteristic graph. This whole section which we consider this is the VI characteristic graph of the FET. Now our today's main consideration is transfer characteristics. So what is the transfer characteristic of JFET? Okay, and channel JFET. So here ID we can summarize as IDSS, which is the maximum saturation current of the drain. Okay, IDSS. Somewhere it is in some books it is written IDS, but for better understanding we consider it as IDSS, which is maximum drain current or maximum drain saturation current. Okay, maximum drain source saturation current. So this is DSS, drain source saturation current. And here the graph is between VGS and IDSS. So what is happening? We know that semiconductor device doesn't follow V is equal to IR. So V proportional to I, they don't follow. And, and when V proportional to I, we know that a linear graph between I and V are formed. So this is a non-linear graph. It means this is not happening in semiconductor device. Any semiconductor device, if we talk about diode, BJT, FET, MOSFET, everything, this linearity we will not achieve. So this is a parabolic graph. Okay, this is non-linear. Current is increasing or decreasing in a manner which we consider as a parabola. So this is a parabola and non-linear. Exponential also we can say. Exponential, half parabola. Okay. So here what is happening? This is the value of VGS. Okay. So when VGS is 0, this point is 0. When VGS is 0, we are getting the maximum current. IDSS maximum. Okay. When VGS is 0, the maximum current we are achieving. Here also we can see that when VGS is 0, first case maximum current we are achieving, the maximum saturation current we are achieving. Similarly, here also when VGS is 0, this is 0 point for VGS. So we are getting the maximum IDSS. So here maximum IDSS. Okay. Now what is happening? The current is gradually decreasing when we move forward this. Okay, when VGS is more negative, let's suppose -1, -2, -3. Similarly, when the VGS is increasing, negative reverse bias is increasing, the current is gradually decreasing. Okay, current is gradually decreasing and flowing in this section. Okay, when this current is here, when this current is equally meeting to 0, this is a 0 level, this is a 0 scale. So hypothetically it is 0, but hypothetically we can assume it's 0 so that we can find the current equation from that. So hypothetically it is 0, but somewhere it is not 0. Okay, in semiconductor it is not 0, but it is 0 if we are considering according to the theoretical prospect. So it is 0 this voltage Vp. Okay, the current IDSS max, which is maximum current, is 0 at this voltage, which is Vp. So when VGS is 0, VGS is increasing. Let's suppose this is -4, Vp is -4. At Vp equal to -4, this IDSS is 0. IDSS is 0. So this value we consider as pinch off. Okay. So at pinch off, the IDSS, which is the saturation current, is 0 in case of transfer characteristics, where transfer characteristics is graph between VGS and IDSS. Okay. So here what is happening? At a particular value, which we consider at Vp, which is the maximum negative value from where the current is 0. The ID current is 0. No current will flow after that. Okay. So this is the meaning of this transfer characteristics, that first we are drawing it between IDSS and VGS and we are making a point, we are getting a point Vp from where the current is 0. After that the current will not increase. So this is the point where the current is 0. So this is the definition also. Pinch off voltage definition also we can consider it. Transfer characteristics also and pinch off voltage definition. After that current saturation in VI characteristic. After that current becomes 0 in transfer characteristics. So these two characteristics are little different from each other. Why we are studying these characteristics? Okay. Although I already told you that semiconductor devices doesn't follow 100% of that, then why we are doing? Because they didn't show the linear graph. Why we are doing? Because we have to find the current equation, so that we are discussing the transfer characteristic and the VI characteristic of that. From that we will get the current. Okay. So this IDSS or this ID current we have to find in our devices. So somewhere we have to maintain a particular criteria that yes, this is VI characteristics, this is the saturation, this is the linear region, this is the active region, and this is transfer characteristics, this is pinch off, and after that channel off. So that we are getting the equations of the current. So we will discuss it now. Equation of the currents. Okay. So transfer characteristic is a graph between VGS and ID. Okay, graph between VGS and ID where VDS is constant, drain to source voltage is constant, and we are plotting the graph between VGS and ID. Obviously, VGS is varying in nature. Now, what consideration we do that when VGS is 0, ID is max, which is considered as IDSS. drain to source saturation current, which is IDSS, ID max we can consider. And the second, when VGS is equal to VP, which is pinch off, then ID becomes 0. So what is happening? What is the second criteria when VGS is achieving VP? So here in diagram also, in circuit diagram of FET, working operation circuit diagram of FET, we also see that when the VGS is very very high, let's suppose -4 when -5 volt, then what is happening? The width of the the depletion region width is increasing abruptly. If the width is increasing that much, that very narrow channel or no channel is left. In ideal condition, we see that these two are touching each other. We know that they will not touch because of the electrostatic repulsion force, but assume that, so that we can find the ID value, find the particular value, something we have to assume for finding the best appropriate value of ID current. So we assume that these two channels in FET, if this is FET, these two channels FET, these depletion region of these two channels or FET of FET are that much touching each other, so that the channel here, the channel which was in between is stopped flowing the current. If it is stopped flowing the current, that means the value of ID becomes 0. Okay, ID becomes 0 due to this depletion region width increase. And why this depletion region width increasing? Because we are increasing the VGS, the negative voltage toward the gate source we are increasing. So this depletion region, the width of the depletion region is increasing. Okay, so then this channel between this is narrowing. We can see this in diagram also. So this is the diagram here. Okay, here when we increasing the VGS more negative, then this depletion region width is increasing. When more reverse bias, this depletion region width is increasing, and a certain level these two are trying to touch each other. Okay, and no path left between drain to source, so that the current will flow. So in this case, we consider that voltage as VP or pinch off. After that, the ID current will become 0. Okay, so this is the meaning of ideal transfer characteristic, that when VGS is equal to VP, the pinch off, after that the ID current will become 0. And we consider those criteria to find the appropriate value of the ID current. Okay. Now here, so this is the value of ID current. IDSS 1 minus VGS upon VGS off, which is VGS 0 square, whole square, and the second is IGHS when VGS is equal to VP whole square. Okay, so these are the two equations. These are the equation of we know that these the diode equation BJT and all these equations are derived from the Schottky diode equation. So this is the significance of that also, that we are directly putting the values, and the derivation is very high, which is beyond the scope of basic electronics. So this is the Schottky diode equations. We are applying it here because they are PN junctions also. And similarly for parabola also, for parabola also same equations we are considering. So this is either ID current when VGS is off or VGS is 0, or second one is when VGS is equal. Current equation which we get from the transfer characteristic of the JFET, as given JFET. So here IDS is 1 minus VGS upon VGS off condition whole square. Off condition is at 0. And the second one is IDS is 1 minus VGS upon VP whole square. Okay. So these two conditions are directly derived from the Shockley equations, Shockley diode equations, Schottky diode equations and Shockley diode equations. We know that William Shockley is the scientist behind the transistor bulb. So the derivation of this is not in our course, so you can directly understand those equations, what is happening, IDSS and ID, and 1 upon VDS, VDS of square. Similarly, ID equal to IDSS 1 minus VDS VP whole square. Okay. So I hope you understand this class, and I will see you in next class. Till then, subscribe and watch. Bye bye.